Current states of neuromorphic AI chip development. Neuromorphic computing seeks to emulate the neural structure and operation of the human brain. To develop computational architectures that are both energy efficient and capable of complex, autonomous processing. This approach uses a combination of analog and digital electronic components to mimic neurobiological architectures present in the nervous system. 1. Technological advancements, materials and design exploration of advanced memoristive systems capable of mimicking the synaptic actions provides a base for self-learning capabilities. Graphene and transition metal dichalcogenides are also studied for their exceptional electrical properties. Suitable for neuromorphic applications. Neuromorphic sensors. Development of sensors that operate neuromorphically, providing direct sensory data input into neuromorphic systems. These sensors mimic biological senses like vision and hearing. Hybrid CMOS memoristor chips. Combining CMOS technology with memoristors enables more dense and efficient chip designs, allowing for better integration of memory and processing units. Energy-efficient synapses. Innovations in creating synthetic synapses that use significantly less energy than traditional transistors in digital circuits. Optical neuromorphic devices leveraging the speed of light to improve the communication speed between neurons in neuromorphic chips. 3D integration. Stacking multiple layers of neuromorphic circuits to achieve higher neuron densities and closer mimicry of the human brain's three-dimensional structure. Adaptive plasticity techniques that allow neuromorphic devices to adapt and learn from new information. Similarly to how biological synapses strengthen or weaken, time-based encoding using precise timing of pulses to encode information, which enhances the efficiency of data representation. Quantum neuromorphic computing. Merging quantum computing principles with neuromorphic computing to potentially solve complex problems faster. Biocompatibility. Research into making neuromorphic devices biocompatible, allowing them to interface directly with biological tissues. 2. Leading players and innovations. Intel's Loihi. Intel's advanced neuromorphic research chip, Loihi, simulates up to 1 million neurons and 130 million synapses, demonstrating adaptability in learning and self-optimization. IBM's True North utilizes a network of 1 million neurons to perform complex pattern recognition and sensory processing with extremely low energy consumption. HPE's Product Engine. A chip designed specifically for matrix and vector computations, which are central to the operations of neural networks. Samsung's Spinnaker. A neuromorphic processor that can model more than 1 billion neurons. Qualcomm's Zeroth. Designed to process real-time data for machine learning directly on the chip, reducing dependency on cloud-based systems. NVIDIA's neuromorphic system. Though primarily recognized for their GPU developments, NVIDIA is also pioneering in integrating neuromorphic processing units into their systems. University of Manchester's Spinnaker 2. An advanced version that aims to simulate neuron activities more efficiently and at larger scales. BrainChip's Akita. A neuromorphic system on chip that brings AI processing capabilities to edge devices, minimizing data processing latencies. MIT's Artificial Synapse. An innovation that could provide the necessary flexibility and learning capability for future neuromorphic networks. DARPA's Synapse program. A government-funded initiative to accelerate the development of neuromorphic technologies and brain-inspired systems. 3. Applications and impacts. Robotics. Equipping robots with neuromorphic chips to process complex tasks like navigation and manipulation in dynamic environments autonomously. Healthcare. Monitoring devices that monitor neurological activities and predict anomalies like seizures in real time, potentially offering life-saving insights. Smart cameras. Utilizing neuromorphic chips to process visual data on the fly, enabling real-time object recognition and situational analysis. Wearable technology. Integration into wearable tech to process physiological data continuously and predict health issues before they become critical. Automotive sensors. Enhancing the capability of self-driving cars through faster and more efficient processing of sensory information. Voice-assisted technology. Improving voice recognition systems to be more responsive and accurate in real time. Environmental monitoring. Application and devices that continuously monitor environmental parameters, such as pollution levels, using low power. Security systems. Enhancing security monitoring systems to identify and respond to threats autonomously. Internet of Things. IoT. Enabling more efficient and intelligent processing at the edge, reducing the need for data to travel back and forth to the cloud. Aerospace. Use in aerospace applications for processing vast amounts of data from satellite sensors in real time, directly on the satellite. 4. Challenges and limitations. Scalability. Scaling up from laboratory prototypes to full production models remains a significant challenge due to complex integration and high production costs. Lack of standardization. The absence of industry-wide standards in neuromorphic computing leads to compatibility and interoperability issues. Hardware complexity. The complexity of designing and fabricating neuromorphic chips that accurately mimic neuronal functions is a significant engineering challenge. Software development. The need for new programming paradigms and development tools that can effectively exploit the asynchronous, parallel processing capabilities of neuromorphic chips. Testing and verification. Establishing reliable testing and verification methodologies for systems that learn and adapt continuously. Thermal management. Managing heat dissipation in densely packed neuromorphic chips, especially in large-scale implementations. Power supply issues. Ensuring consistent and reliable power delivery in systems where power usage can fluctuate dramatically based on computational demand. Data privacy. Addressing concerns related to data privacy, especially as devices become more integrated into personal and sensitive areas. Long-term reliability. Ensuring the long-term reliability of neuromorphic systems, particularly in variable environmental conditions. Public acceptance. Overcoming public skepticism related to AI and automated decision-making systems, especially in critical applications like healthcare or security. Future trajectory. The trajectory of neuromorphic computing points towards a synthesis where devices not only collect data, but also interpret and act upon it autonomously. As the field matures, we could see a dramatic shift in how computational tasks are approached, potentially leading to a new era in technology where artificial intelligence closely mirrors biological intelligence, both in form and function. This futuristic technology is set to revolutionize industries, pushing the boundaries of what's possible with artificial intelligence.